Hello engineers, and today we're going to be talking about gears, pulleys, and sprockets. So they're very similar to simple machines in that there are mechanical advantages associated with them, but we're going to talk today about gear ratios, the advantages and disadvantages of gears, pulleys, and sprockets with chains. So let's get started. The first thing, what gears, pulleys, and sprockets are typically used for. Number one, you can make something spin faster or slower. You can change the direction, like shifting from forward to reverse. You're engaging one more gear in your transmission. Or you can change how much power you have. I mean, that kind of goes along with changing the speed. You know, like think about your bike. If you've got a 5, 10, 15, 27 speed bike, you can change how fast, and at the same time, you're changing how easy it is. Under here, this is a transmission, the inside of a car's transmission. This is a pulley that's on a lawnmower, so you can see that this is what's spinning the blade, and this is the back end of a motorcycle, which is turning the rear tire. Gears have what are called interlocking teeth. So we have a word for that. When the teeth interlock very nicely, we call it they are meshed. So gears, they're meshing. So if they're not meshing, then you get that rattling. That's what we call meshing. We have what's called the drive gear and the driven gear. So it's like simple machines in that there's an effort one and then there's a resistance. So one of these gears we're going to be putting the effort into, and then down the line one of these gears is going to be doing the work. So the driven gear would be the one that you're putting your effort into. So here's a couple of examples of gears. Mating gears always turn in opposite directions. So if you ever see a picture of gears, what I like to do, I like to take a marker. It will help me, and I do the letter S, like I'm going to slalom. Many of you probably don't water ski, but watch this. I would go like this, and then I would go like this. So I can tell which direction the gears are going. Now I'll do it over here. So I'll go like this, like this, like this. So I can tell if this gear is spinning clockwise, doing this S motion, I can tell which direction that gear is going by doing an S. S-ing my way, slaloming my way around these gears will help me determine which direction gears are traveling. An idler gear. This red one in this second set is called an idler gear. It's a gear in between two gears. They call it, sometimes you'll have pulleys this way, they're called idler pulleys. So putting this one here allows the drive and the driven to be turning in the same direction. So mating gears always have the same size teeth, physical shape, and all that other geometry associated with it. Gears. RPMs of larger gears are always slower. So this red and the blue one. So when you're looking at, if you're counting how many times it spins, the blue one is going to spin, because it's bigger, it's going to spin less times than the red one. The smaller gear has to spin more times. Now, in the next thing, it says gears locked together. So the yellow and the blue, these two gears are locked together. So they're always going to spin the same direction, and they're always going to spin at the same speed. So blue and yellow, they are locked together and have everything the same. Same everything. The red and the blue, since they're not locked, the blue one's going to spin slower. It's going to spin in the opposite direction, and so on. Gear ratios. We can find a gear ratio from a lot of different ways. You can count the number of teeth. For instance, this one right here, this blue one, you would count how many teeth, or the diameter. You could count how many. You could physically measure the diameter. You could go from outside of the tooth to the outside of the tooth. Or you could go from the inside to inside, as long as you're doing the same thing on both of these gears. You could measure the speed, how fast they're spinning. Physics people would maybe remember this. This is the letter omega. Greek letter omega, which means angular velocity, how fast it's spinning in RPM, or radians per second back in the day. Or you could measure torque. This is the Greek letter tau, and it stands for torque. So for instance, in this blue and red scenario, the blue, if you were to count these, there are 12 teeth on it. And if you counted the red one, there are 6. So this has 12 to 6, so 2 to 1. You can measure the diameter, 4 inches to 2 inches. So that also has a advantage of 2 to 1. The speeds. Now the speeds are opposite because the big one, the one that has lots of teeth, is going to spin slower. Again, 2 to 1. 40 RPM to 20 RPM. And then torque, 2 to 1. So finding the gear ratios, you can use any of these equivalences. These are all the exact same thing. So you can count the number of teeth on the output, divide by the number of teeth on the input. So you'll see that the out over the in, out over in, out over in, all except for speed, out over in. The only one, the speed is the opposite because the more teeth it has, the slower, so that one's reversed. So we can find gear ratios knowing any of these things. So, for instance, it says, what is the gear ratio between gears A and B? So what we're going to assume is gear A is the input. So the gear ratio between gear A and gear B. And remember, it's out divided by the in. So if this one's the number of teeth out divided by the number of teeth in. So that would mean our output is going to be B. So that's going to be 12 divided by 20. So 12 divided by 20 is the same thing as 6 divided by 10, which is 0.6. So the gear ratio is 0.6 between A and B. What is the gear ratio between gears B and C? Same thing. It's going to be the number of teeth out, which is going to be 5, divided by 12. So 5 divided by 12. Mr. Hare needs his calculator for that one. 0.42. Put a 0 there for two significant figures. What is the gear ratio between C and D? So my output is going to be 20. And my input is going to be 5. So that has a gear ratio of 20 over 5 is 4. So pretty easy. Just count the number of teeth, assuming that my input is A. What is the total gear train ratio? To find the total gear train ratio, what you do is you multiply all those together. So what I would do, I'm going to take 0.6, multiply by 0.42. Now I'm going to, if you're actually following along with me, it's 0.416 repeating. I'm going to use that exact number. So I'm going to take 0.6 times 0.416 repeating times 4. And I get 1. So this times this times this, multiplying them all together, the total gear ratio is 1 to 1. And that's weird. If you look at it, it turns out all you have to do, if this is the input, so again, doing my snake around, so this way, this way, this way. So this one's going to spin the opposite way. It's going to spin the opposite way at the exact same speed, the exact same torque, everything. And really all you needed to do, the real secret here, is you look at the number of teeth on your input, you skip over all these, and you look at the number of teeth on the output. Since they have the same, it doesn't matter what you put in between. The input and output will spin the same speed. So if this was 40, everything would go accordingly. You wouldn't have to take into account gears B or gears C. You only have to look at the the last one. And then if the last gear had 40 teeth, what would the total gear ratio? Remember, it's out divided by in, so 40 divided by 20. This would have a 2-to-1 gear ratio. Gear ratios in compound machines, they're very similar to mechanical advantages in that you can find how much force that you get out. So you take, if you remember back to, what is it, actual mechanical, I'm a deer, am I free? Actual mechanical, it's the force in, force out sort of thing. You multiply, you would do the same thing with gear ratios. So if you want to know how much torque you're gaining, for instance, like me, when I was doing the blinds in my back room, I knew I needed a certain amount of torque. So how big of a gear can I make so that I have enough force to lift those blinds? And again, in compound machines, you just multiply them all together. Like I did back here with this one. I multiplied them all, but all I had to do is the front and the back one. Now, here's a compound machine. I've got, boy, it looks like I've got a wheel and axle right here because I have a long distance that I'm turning and then a wheel and axle, and then I have a gear ratio, and then I have another wheel and axle. So this is three simple machines here tied together to make one compound machine. And you're noticing right here, I'm putting my effort force on this. So if I push up, I'm going to push up on this right here, which is going to turn this that direction. And if this one turns this direction, using my snake method, it means that this is going to turn that way, and so then this is going to end up moving up. So it's going to end up going up, and that's why the force of resistance is pushing down, because it wants to go up, and so the resistance is opposing that. So this thing will also go up. So that's kind of what's happening when I look at this thing from like far away. Like what's going to be going on if I push this up? Okay, that other one's going to move up. So we're going to try to find the total mechanical advantage of this whole thing. So we're going to find the mechanical advantage of each of these separate simple machines and then multiply them together. So, and you can see that this is highlighted here. So this first one is my first mechanical advantage. And it looks like we're going to do the ideal mechanical advantage because we're only given distances. So we're not given forces just yet. We're only given distances. So remember, I'm a deer. I'm a deer. So the distance of my effort is 4 inches. The distance of my resistance is going to be this radius right here. So this has a radius of 1.5. So 4 divided by 1.5, I think that's like 2 1/3. Yeah, 2 2/3. So 2.7. That's mechanical advantage number 1, the ideal mechanical advantage. So now we're going to find the next one. That's our gear ratio. So we're going to find the gear ratio. Again, this one is going to be the input. So to find the gear ratio, it's the number of teeth out divided by the number of teeth in. So my output is going to have 24 teeth. Or maybe I could just, yeah, we'll do the teeth. That's fine. So my output's going to have 24 teeth. My input is going to have 60 teeth. So 24 over 60 is the same thing as 12 over 30, which is the same thing as 6 over 15, which is 2 over 5. I'm just going to go 24 divided by 60. 0.4. So this has a mechanical advantage of 0.4. And now we're going to do the third simple machine here. And that's going to be another wheel and axle. So remember, I'm a deer. So the distance exerted over the distance resistance. So the distance of exertion, So again, this is where the input's happening right here. So my input distance is this distance right here. And then this is my resistance way over there. So my input distance is the radius, is 0.6. And then the distance of resistance is 4. So 0.6 divided by 4 is going to be 0.15. So now to find the total mechanical advantage of this entire system, what I'm going to do is multiply those three things together. And boy, I can't remember them. It was 2.7, 0.4, and 0.15. I get 0.16. And again, I use the actual, it's like 2.6 repeating for this one. So 0.16 is my total mechanical advantage. This is a pretty poor mechanical advantage. What it is, it's not a force advantage. This is a distance advantage. So even though I'm losing like 80% of my force, I'm increasing my distance. So if I push this thing up like 1 inch, this thing's going to go up like 8.7. You know, it's going to be a huge, very, very fast acting motion there. Compound gear trains. So what happens if you have, here's our driver, and then you're hooking it up to this yellow one, and we can actually figure out the mechanical, or the gear ratio just by counting. Let's see. So it looks like these white ball, like the white ones come together. Yep, they looks like they meet. So let's count how many times the green one goes around the next time this white ball comes around. Ready? Well, I missed it. 1, 2, 3, 4. So this looks like it I mean, if they're doing this to scale and everything, this looks like it has a gear ratio of 4 to 1. Now what we're going to do is we're going to tie this blue one on. So these are on a fixed axle. So these have the exact same speed and torque and everything. And then we're going to mesh that with the red one. And then looking at this one, let's maybe see if we can figure out the gear ratio here just by looking at it. Oh boy, doesn't look like they touch. There they go. So looks like it goes around 1, 2.5. That's it. Looks like 2.5. 2 middle gears are a common axle. All right. So first question, what is the gear ratio? And now they're giving us the teeth. What's the gear ratio between gears A and B? It looks like 4 to 1. Remember how we guesstimated just by counting, looking at the angular velocity? But now we can actually see it's the out divided by the in. And it's 40 teeth to 10 teeth. So it is 4 to 1. Looking at the other one, it was 20 to 50. So it was 2.5. So the N out. The number of output teeth was 50. The number of input teeth is 20. 2.5. So the gear train of the entire thing, here's where you multiply them together. 4 times 2.5 is going to be 10. So this has a 10 to 1 gear ratio on the whole thing. So you can get a magnification of 10 in both your speed or your torque, depending upon which one you drive. Belt and pulleys. So they're similar to gears, except that they just have a pulley that goes in between them. So again, it's the same thing. It's out divided by in, except for the speeds, because bigger ones spin slower. Chains and sprockets, they're the exact same thing, where you have out divided by in, except for the speeds. That's where it's reversed. Yeah, they actually give me stuff here. So this is the input. This is the output. So it's going to be 6 divided by 2. So this has a 3 to 1 gear ratio. This one here, 3 to 1.5. Out divided by in. This is going to be a gear ratio of 2. Belts versus chains. They have pros and cons to each of them. So a belt, one of the advantages of a belt, number one, is it's quiet. If noise level is something important, you maybe want to go with the belt. It doesn't require lubrication. It's inexpensive. It does stretch though. So like there's stretch. It's light. You know, if weight is a big issue. With chains, there's no slip. It's stronger. It's more expensive. It's heavier. If you need to transmit a lot of force, chains are where it's at. You know, so there are advantages and disadvantages to every kind of pulley and chain, and sometimes they have hybrids. I don't know if you've ever seen sometimes different timing chains. They have aspects of both the chain and the pulley. So there's a belt, but it's got like teeth on it. It's really kind of neat. So kind of the comparison, the compare and contrast belts and pulleys. So that's belts, pulleys, and gear ratios in a nutshell. Basically, it's just teeth. Remember, counting the teeth, counting the speed, counting the diameter. It's out divided by in every single time, except for when you look at speed in all of these things.